And what we do is we investigate things that go from femtoseconds, which is 10 to the minus 15th of a second, all the way up to seconds and what I say kiloseconds. So, 18 orders of magnitude in time we can investigate. And there are important processes that occur on all of these time scales that are relevant to physical and material and biological systems.
As director of Ohio State's Center for Chemical and Biophysical Dynamics in the Department of Chemistry, Terry Gustafson manages a lab full of spectrometers driven by lasers and capable of producing data for a wide range of researchers.
As you might imagine, you really can't go into Best Buy and pick out a laser system that will do this.
And even if he could buy the lasers off the shelf, the Geek Squad probably couldn't provide the optics, computers, and other gear that go into such sophisticated instruments.
So we generally construct our laser systems from scratch, and because of the unique combination of things that we have to put together to do these, we write our own software and use our own computer interfaces to acquire data. And oftentimes it also involves writing our own software for processing the data, because we will end up with very large data files that have to be dealt with in specific ways in order to translate them from one type of data domain to another type of data domain.
So the experiments are all about the data, and the link between the instrument and the data is software, much of it written in the lab.
It's absolutely critical. But as you can then imagine, you write it in one operating system for a computer, and 3 years later, the operating system has been modified, so now we're working with an older computer.
The custom software is often written by one graduate student and maintained by one or more later graduate students. A researcher would like to see a return on his or her lab's investment in rewriting software, such as added features, not simply compatibility with a newer computer or operating system.
It's a common problem even for those who work in an office, but it's the same challenges we have, but then kind of restructuring our programs also then involves rewriting many of the programs so that they can operate rather than, some of the older systems we have still use serial ports and parallel ports to access the instruments.
Mike Reed, Senior Systems Manager, supports all computer users in the Department of Chemistry, but knows how much researchers rely on their computers.
So they have all of the same issues that, like say, a general user would use, an administrative associate. On top of that, they have these very unique and specialized challenges that they're faced with.
There are many challenges to keeping these dedicated and unique computer programs operating to keep our experiments going. So, and it's expensive on many fronts because it shuts us down for periods of time where we can't use the instrument, which is not good.
One of these challenges is the reliance on one-of-a-kind computer systems. A problem with such a computer stops research, which can impact the likelihood of getting future funding.
We often see the IT landscape is shifting. We have new security requirements that we're required to follow. We have different pieces of hardware or software that we've put in place, whether it's a firewall or a new server. And as that IT landscape is constantly shifting, we have to have in mind all of the solutions that we currently have in place and make sure things keep working the way they should.
Communication between researchers and anyone who can change the IT environment in which researchers work, such as by implementing policies or altering network performance, is crucial.
We very much rely on the computers. We couldn't begin to take any of the data that we have without having having it computerized. I mean, it's just impossible.